just look on a map and try to envision how will it appear sort of down between the features. So it's we have been sending people all over the world to make drawings and just to make sure that the maps show the right things. And also to make sure that meteorology stations we used were still there, where the data showed they should be, or they have been changed, talk to people and make sure that the quality was okay. Now Google to some extent replaces some of that travel. And then aside from Google, everything that can provide information about the characteristic of the surface. And then with data and models, we can just compute. And we can do it various ways, and we have, as I said, made a systematic way, but you don't need to do it systematic. A lot of the things, you don't even need to do it numerically, because a lot of the models I described about are simply analytical formulas which you can sort of multiply to each other. So it depends on needs and possibilities. But what we typically do is that we say, now we want to find the wind power at a certain station, at a certain point. So the left-hand side of this figure show what we do with the measurements nearby. And if we start down in the bottom, we start by correcting it for obstacles, reducing the influence of roughness to a standard, and correcting it for the upper, for the topography, the undulation of the landscape. And then we come with a standard formulation for the wind, which is not influenced by all these features there, ideally. And then we turn to the wind turbine, and then we say, how do all these things look for the wind turbine, around the wind turbine? How does the terrain look? How does the roughness look? Or roughnesses, many roughnesses? And how are the obstacles around? And then we go the other way, and then we compute, again, something that looks like the former one, a wind distribution and a direction distribution, but now should be valid at the point of the wind turbine, and of course at the relevant height. The relevant height is what we call the hub height, and that's where the axes are sitting, the rotation axes are sitting. That's sort of in the middle of it. And this is information about how that should look. We can just say we have the wind distribution in all directions. The table shows 12 directions, and then the information about the distributions. And down there are just the marking distribution. So now we have all the information about the point where the wind turbine should work. And then we just multiply by the power curve, and then we have our estimate of how much will have to produce. And then the one who decides, say, it's not enough, I won't do it, or give me 10, or whatever, depending on how the economy will look for him. So that was the way it started, actually in the middle of 1970s. And here, how does it work? Has it worked? Now, in the upper one, we have all the blue countries have used the method. And whenever people use the method, we get feedback in, did it work? And especially when they use it to build a wind turbine, because then they can also, the following year, do this wind turbine actually produce what was said? And what, if not, why not? Was the wind turbine at fault? Did the wind speed actually reduce compared to the climate mean value which we were accepting? Because remember, we use a climate average value. And so how long should it be? And typically it should be less than 10 years and more than 2 to 3 years. It shouldn't be too long, because we are not trying to predict the past climate. We are actually trying to see how will the next ESB. And so if you make the series too long, it's weighted by too much by how it was far in the past. So from all these places we get, it's actually to a center, and there comes in information about how did the prediction work and what should be changed, is anything wrong, and things like that. So you could say it's not a really scientific evaluation, it's more what you would call an industrial maturity. Whenever something is wrong, it's repaired a little bit and better and better. The red, including Russia, have what we call a national wind atlas, where all the stations one have been able to put their hands on has been integrated, and so there is a wind atlas, and a wind atlas is a book, and then it's also a model system with data, and the model that allows you to interpolate between the data. So you can say, how will the wind look at my particular spot, if I can describe this up. I don't think anyone has used it in Russia. And in West Europe and Egypt, it has been used extensively. Algeria, also not. But all the blues are places where it has been used to evaluate siting of wind turbines. Now there are limitations to this data extrapolate, and notice it's a way we extrapolate data. We don't really model very much. We model these differences between two stations, differences in obstacles, orography, and roughness. That's the only thing this modeling I have talked about. So what we demand of the station and the wind power point is that they should sort of, in general climatological thing, be similar. The geostrophic wind should be similar, and you should, if you model things on land to, from a station on the water or vice versa, you should, in those cases you really need to take account of that the heat flux over the two surfaces are quite different. That's also included in our model. But that's the only place where we have temperature in. Then it's a linear effect. All these obstacles, roughness, things, they just multiply upon each other. Or you could say the small changes add. So it's linear in that sense. It's mostly based on neutral stability, boundary layer model, aside from this water-land limit. And this is probably not working so well overall. And then we also have roughness. It doesn't vary. We fix the roughness. And you who have with oceanography to do know that roughness of the water surface should go with U star squared. And of course it can be a lot more complicated. And you from Russia know that it does depend on if you have snow on the surface or not. So seasonal variation should be included. But it was not included at that time because this was actually mostly focused on Europe and Western Europe and part of US. And then if you start including all these things, it becomes a lot more complicated. So now what is all these limitations, or some of them are broken. And one of the things that will often be broken is that good data are not broken. Then we can today use the meteorological weather forecast model. And we have these used numerical weather prediction systems, climate prediction systems. Some of them are global, and they have many benefits, but they don't focus on one point. And we need to be able, in the end, we need to be able to focus, when compared to the measurements, we need to be able to focus on a measuring mast, where the measurement is conducted, or a wind turbine location where the wind turbine is thing. And then it doesn't help that we tell them a 10 by 10 square kilometer area average, because this is not relevant for these things. So in the end, we have to be able to focus. So the way it's done is what is called dynamic downscaling. So we start with a large scale, and then we use mesoscale, and then we go small scale. And you can do that today because of the computers are advancing so fast. But still there are problems. Now I'll tell you what is 3/4 of an hour. When did we start? Okay, fine. I will tell you now about two. It's a smaller part of the lecture, so those getting restless can relax. And there are several other examples. Now I show you two examples of these weather or wind prediction things that use numerical weather prediction models. And one is from a central state in Africa, which did not have many good data, although it did have few. And then also it was difficult to get there. You know they are fighting now, and in the beginning of the project, the fighting was sort of starting, so we could not go everywhere and these kinds of things. That has actually been the problem. Many of these places we have been there. Good. So we start with a global data set. And today we have the global data sets. It's called the reanalysis data. And what it really is it's an accumulation of all, or it takes all the measured data which are stored, and then it treats them as they are going to be used. Each set are going to be used as initial conditions for a weather forecast model. And you know, they use measured data. They have to use measured data, but they cannot take them squared. So they do a thing that they use the measured data to get initial conditions in all grid points in the model. And that of course takes the model run backward and forward. So what comes out of that, instead of a dispersed set of measured data, you get a climatology of all the meteorological variables in each grid point of the model that has been used to generate it. And that's quite a few grid points. The drawback is that now it's not really raw data anymore. It's looked through a specific model. And every 10 years or so, when the models improve, they take the whole series again and use the new models to make these data. But here we have some of the older ones. The American, 1948 to 1999, and I think they are around 2009. So it's a real long series, and it covers the whole world. And here is, it has 2.5 times 2.5 degree of resolution. That's about a little less than 300 kilometers square. And you can see this is very far from a 1 point measure. Then it reports every 6 hours. It has 15 levels, all places where you have climate data now. And this you can use. This is the climatology which you can use to take a subset out, and in this special case we use the geostrophic wind profile and then the potential temperature at several levels. But you need to get down up in resolution downscale. And you cannot use the model there or the data there. You have to use another model, which can then use the large scale model as driver. But then for the new model, you need to know below the error, it needs, of course it needs information from the large scale model, but it also needs surface information now in the proper resolution. It cannot use the large scale surface, it needs a resolution that is corresponding to the model. With this model there, the grid size was 7.5 kilometers. So it needs the surface information. And the model is called the CAM, and this is just a picture of it. And so it has a large-scale driver, but it needs a terrain feature. And there you can go in these international books and state. For the terrain feature, we do use the space shuttle. They have made resolution in 1 kilometer resolution all over the world. Surface roughness, we used something called the United States Geological Survey Land Use Cover Classification Scheme. And they have also one resolution, so they tell you all over the world what is on that particular surface. And so then we have everything. Then this is the terrain. This is actually made, it doesn't matter so much. You can see the black. There's a black borderline, but of course meteorology doesn't really collect concern about political borders. So we took this area there. We had the terrain from the space shuttle, and the roughness comes there. What you see there is mainly is the northern part is desert, and the southern part is actually mostly rainforest, and you have various things in between. And I won't go into the selection, but this is the roughness we got out. And now comes the thing, now we could run it. We could run this mesoscale model for every set of large-scale information we have. If you have 30 years, 4 times a day, it's 43,800 times we should run the model, and we cannot do that. Still, we cannot do that. So now we do the thing that is always done in this connection. You select characteristic situation, their probability, and then you run these characteristic situation. So there's 3 areas over there, and each there are sizes, there are 3 mean speeds, there are 12 directions, there is 5 food number, that means normalized temperature gradient measures, and then there is information about the frequency, how often each category is appeared. The important one sums up to 130 about, and then you run all these 130 with the mesoscale model, and then you average properly, then you have the mesoscale wind resource. Again, it's smaller scale, 7.5 kilometer, but it's not a point measurement. Then you go in and take this old wind atlas method I took before and use the mesoscale result to go down to even finer scale. And now you can talk about the wind resources that are given from. Here we have some of things. And in the end, we compare data and prediction. And now this is just one example, and you can see they're not quite similar, a little bit similar. And then for the stations we have, you compare what you predict and what's actually measured. And then you can make a very long discussion, or very short, about what that means about the quality. Which I will not do here. It's like the old wind atlas, it's good enough to continue. So, the numerical wind atlas method has been very practical, and all the modeling, most of the modeling development is now anchored in the meteorological community, which is nice because they're developing models all the time. There is a principal problem of assigning roughness. We already had that with a fine scale model. I mean, we could say the roughness for this terrain, for that and that, but we could not really prove it. And now we have several models that are seeing the same terrain, and the roughness assignment has something to do with the fluxes. So they should have different roughnesses that somehow should sum up to that they have the same total momentum block being the same. And it's not a result thing, but it technically results. And then I just show you the last, which is maybe more relevant than Africa for you, namely the Finnish wind atlas. And if you can see, where we have the American data with 2.2 degrees resolution. Then they have data from the regional range weather forecast center. They use the Scandinavian, Nordic, North European weather forecast model to provide climate data, now with a resolution of 7.5 kilometers, which was the one we achieved with the mesoscale. But then they had another mesoscale model hitting below, and now they got down to, it's called a home, to a resolution of 2.5 kilometers. And then they could give a resource estimate for 2.5 kilometers. And then again they could use the wind atlas, the spatial focused method, to come down to the point measurements again in the end. So it's sort of characteristic. People do quite different things, but they're very similar. But they have one level of models more than we have. But again, you start with large scale to get the climate, and then you focus as much as you can. So this is the finish. So a wind atlas for an area is a data model system. It's a combination of a model system of data available, which are controlled and acceptable, that can predict wind energy production at any location within the area for a given wind turbine. This is what it is. So it's not a map. And experience shows that decision about if, when, and where to erect wind turbines has been very much helped by having this information available. So people, if they just are told that it blows more there than there, they say it doesn't matter. I want to know how much money I can run in a year. And therefore they need to know an estimate of the energy production. And for all these meteorological modeling, as we all know, there are many assumptions, simplifications, and even individual preferences, and it develops constantly all over the world. And therefore it's necessary to have some data to compare to keep them a little bit trustworthy. Then I would say thank you for your attention. I hope you understood my Russian.
Thank you very much. Question?
I would like to ask about wind atlas. Is it possible to use above seas? I mean, you receive wind speed above length, length roughness, but it's possible to use wind speed above different seas, Nordic seas, or?
Yeah. Originally, we just have wind. The roughness of the sea was taken as 0.2 millimeters, not 0.1 millimeter, 0.2, because it was relatively high winds. And that was good because the way you compare is if you have measuring stations here, one of the quality controls is that you can use the individual measuring stations to predict each other. And this is actually the way it has been done. And we could predict over water and from water inland. If we build in this average difference in heat flux. So remember, we are not predicting cases, we are predicting annual average distribution. So a lot of individual cases get averaged out.
And which resolution is this data?
Yeah. Now we are doing much more complicated over the water because we have these wind turbine farms being put out in the water. And it's not only the roughness, it's also the boundary layer height becomes much more shallow, and get a lot of mesoscale variation over water, which you don't really get over land, so the water is an open issue, actually. We can measure over water now, because we have got the LiDAR technique, which can go 300 meters up and measure level if you have a position. And we have built various remote sensing techniques, which you know about up here also. It's more that there's a lot of focus on water now, simply because there is a lot of, offshore wind farm is really heavily invested. So there's a lot of, you could say, a small fraction is used in our pockets, but for the developers it's just a small fraction. So, and they want to have it right, because it's a lot of money that gets lost if they do things wrong. So over water, the very most important problem is that they change, they're too close. You would think there is all that empty water, but if you see all of the right to waters, still they get the wind farms too close to each other. And so they steal the wind energy, so to speak, from each other. But the water is a big thing now.
More questions, please? And do atmospheric turbulence is a part of the wind atlas or that?
Not the wind atlas I talked about. We have another map called the Wind Engineering Atlas, where you need also information about gustiness and extreme conditions, because not so much to see how much energy there is, but more for design criteria and to know how to run the farms.
But for the design of turbines,
yeah,
could be very important, because gustiness,
yeah.
As I heard, this turbine system use some, like in the car.
Yeah, gearbox, yeah.
I don't know what is the English word.
I think gearbox or clutch.
So it means when there is a strong gustiness or turbulence, the machines start to change the speed, and it may destroy the system. So
and it's not
to be important parameter.
Yeah, that is correct. All the time there are errors that are not really explained, because you could say it's first time. And the machines are also becoming so big that engineers are not experienced enough. And development has been so fast. One of the engineers once told me that it developed so fast in size that when they got all the error messages in from one generation, they were all already multiplied, and for the next generation was much larger. So it was several generations of wind turbine before they could build in the corrections. So it has been in some way technologically a wild period now, which I think maybe will be over. But there is a lot of turbulence, and also in the wind model, because and that is not fully finished yet, because this has to do with how far away should we place one turbine behind the other. Because, of course, when it takes energy out, it's not in there behind it. But slowly it builds up again and available. So it's a kind of optimization. If you get too close, you get too much fluctuations and too little power. But you utilize the area better. And if you get too long out of this, you get low. In cross influence, but you don't utilize the area very much. And so this is a problem there.
Is there any question, please?
Yes, and speaking about chemical, how far we are from this moment when we can finally start building wind farms? We have an update strategy.
farms are being built more or less constantly. It depends on what you mean by we. And in the sea, over the sea, it's mostly wind farms. And I don't really know what the mechanisms are, but there has been, when it started, it was individual wind turbines owned by a few people. And now it's really power plants. I mean, they can be half a gigawatt and things like that. And it's run by the electric utilities. So it has changed a lot. And they are building constantly. And of course they'll get some also bad experiences, which will be costly, but that does not seem to stop it. The reason they go offshore is that, at least in a lot of Western Europe, that there's not a lot of land in Western Europe, and people didn't want all these wind turbines. So they moved them to the sea, where they didn't disturb people so much. And then they took the technological difficulties as they disappeared, or as they came up. And slowly they are being resolved. And so I think there are being built wind farms to the sea, at least a lot in northwestern Europe, also some in the US. I think even the Chinese are doing it. It's also a little bit like a fashion. That everyone has to have a wind farm on the sea.
Any question? Sorry, what is your what is the estimate? What is the fraction of wind energy in the total energy balance of Denmark, for instance? What is the fraction?
15%, I think. It means 1.5. It means 30% of electricity is wind power, and that gives a whole new family of problems because it fluctuates so much.
Okay, so if there are no any questions, so we just again thank you very much for this very interesting, impressive introduction to the wind energy business. So we are going, to develop this laboratory and the institute. So thank you very much.